Welcome to chemistry class again. So in the last lecture we discussed about all these crystal systems and the possible variations in them. In cubic crystal system, primitive unit cell is available, body centered unit cell is available, face centered unit cell is available. These three varieties are available in simple cubic system. Tetragonal system, these two varieties are available. Orthorhombic system, all the varieties are available. Primitive is available, BCC is available, FCC is available, and ECC is also available. Right? Here, from this, it is very easy to memorize, students. So, hexagonal only primitive style is available. Rhombohedral or trigonal only primitive again. Monoclinic has two types of varieties: primitive monoclinic crystals and end-centered monoclinic crystals. There's triclinic. It is not visible, I think. Just wait a minute. Yes, see here. Here, what triclinic in the sense primitive unit cell is only available, right? Okay. 1 minute. In triclinic only, yes, primitive variety is available. Just keep that in your mind. And in cubic system, what are the parameters? Parameters are the sense, what is the relation between edge lengths A, B, C, and what are the relation between interstitial angles alpha, beta, gamma. So, yes, I already explained you on the basis of edge lengths and interstitial angles only these crystal systems are decided, right? In cubic system, yes, it is just a simple cube. A is equal to B is equal to C. Alpha is equal to beta is equal to gamma is equal to 90 degrees. Easy only. It is just normal cube. Normal cubic parameters. For cubic, A is equal to B is equal to C and alpha is equal to beta is equal to gamma is 90 degrees. For this one, tetragonal students, tetragonal, so no change in the relation between interstitial angles. That is what, here in the sense, here in the case of this tetragonal also, alpha is equal to beta is equal to gamma is equal to 90 degrees, but A is equal to B is not equal to C. Just keep that in your mind. Keep that in your mind. That is in the case of tetragonal. They are the parameters. In the case of orthorhombic also, there is no relation change between interstitial angles. Again, you repeat the relation of interstitial angles. Alpha is equal to beta is equal to gamma is equal to 90 degrees. Whereas in the case of edge length students, yes, every edge length is different. A is not equal to B is not equal to C. That's it. Easy to memorize. Easy to memorize in the sequence. CTO. Remarkable, mind-blowing, terrific. Just memorize in the sequence. So for first three there is no angle difference. Every angle is 90 degrees. For first three systems, every angle is 90 degrees. But for first system, all the edge lengths are also equal. A is equal to B is equal to C. For the second system, A is equal to B, but one edge length is different, is not equal to C. Two edge lengths are equal, one edge length is different. For the third system, all the edge lengths are different. A is not equal to B, is not equal to C, and angles are not going to be varied. It is very easy to memorize. When you are coming down to this, here somewhat, in the case of hexagonal students, one interstitial angle is going to be varied. One interstitial angle is going to be varied. That is what? Alpha is equal to beta is equal to 90 degrees. But gamma is 120 degrees. That's it. For hexagonal, one angle is 120 degrees. Rest of the two angles are what? 90 degrees each. When you come to the edge lengths, this one is going to be repeated. A is equal to B is not equal to C. The second one is repeated at fourth one. in case of edge lengths, in case of edge length students, right? When you come to this system, that is what rhombohedral or trigonal system, yes, no angle is equal to 90 degrees, but all of them are equal. Alpha is equal to beta is equal to gamma, but it is not equal to 90 degrees. These variations you have to keep in your mind for objective examinations. For board examinations, these are not necessary if there is a chance to ask in 2 marks questions also. But very easy to memorize. In a sequence means it is very easy to memorize. Right. What is the relation between edge lengths? It is what? First one is repeated here. A is equal to B is equal to C. A is equal to B is equal to C for rhombohedral or trigonal. For these two varieties, last two which are there, for these two varieties, A is not equal to B is not equal to C, and for the last one also, A is not equal to B is not equal to C. For two varieties, for the last two varieties, interstitial angles, edge lengths are not at all equal, right? The last one is very funny. Angles also not related to each one. That is, alpha is not equal to beta, is not equal to gamma, is not equal to 90 degrees. Zigzag pitch count, right? So just you take, yes. In the case of last one is nothing but what? It is triclinic, right? In the case of triclinic, no one is equal. Edge lengths are also not equal, and as well as no relation between interstitial angles. Alpha is not equal to beta is not equal to gamma is not equal to 90 degrees. Yes. But for monoclinic students, last but one, for monoclinic, so here this is somewhat important. Alpha is equal to beta is equal to 90 degrees. Gamma is not equal to 90 degrees. This is somewhat you have to memorize. So these are the parameters of each and every crystal system. Try to take down in your notes, otherwise take a screenshot. You have to memorize in a sequence. CT. Oh, remarkable, mind-blowing, terrific. In a sequence you have to memorize. Then only you can easily memorize these parameters. For first three systems, alpha, beta, gamma, that is, there is no change in interstitial angles, students. Every angle is 90 degrees. Right? A is equal to B is equal to C for the first system. For the second system, A is equal to B is not equal to C. For the third system, A is not equal to B is not equal to C. For the fourth system, second one is repeated. That is what? Yes. A is equal to B is not equal to C. For the fifth system, first one is repeated. A is equal to B is equal to C. For this and this, there is no equality in their edge lengths. A is not equal to B is not equal to C. A is not equal to B is not equal to C. For the last one, it is very strange, very interesting. Every edge length and every bond, every interstitial angle not at all equal to any other one. And the final one is really terrific. That is what? Alpha is not equal to beta is not equal to gamma is not equal to 90. These are what? Parameters of different crystal systems, and different possibilities are there. How many varieties are present means count these: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 varieties are there. Of course, repeated varieties are there, but this is cubic primitive, this is tetragonal primitive, this is orthorhombic primitive, this is hexagonal primitive, this is rhombohedral primitive, this is monoclinic primitive, this is triclinic primitive. Primitive system is repeating, but parameters are varied from one primitive to another primitive, one BCC to another BCC, right? Yes, these 14 varieties are called Bravais lattice. These are all what? 7 crystal systems. We have 7 crystal systems and 14 Bravais lattice. You take the spelling Bravious, Bravis, Bravious, Vais, Lattices. So we are having 14 Bravious lattices and 7 crystal systems. These are the parameters. I think you are all understanding, right? So you have to memorize all the crystal systems, in a sequence. It is very good, very useful for you, right? For simple cube, I am going to give you some examples. For tetrahedral, I am going to give you some examples. For everyone, I am going to give you some examples. You have to memorize them. That is very helpful for your objective examinations, especially, right? For cubic, you take examples NaCl, cubic crystals are some examples I am giving. NaCl, zinc blend, formula is ZnS. These are the examples of simple cubic. For tetragonal students, for tetragonal, white tin, tetragonal students, they are having examples white tin, then TiO2. This is also example of tetragonal, and CaSO4 is also example of tetragonal crystal system. And orthorhombic examples are orthorhombic examples. So rhombic sulfur is the example. And then after rhombic sulfur, KNO3 and BaSO4. Clear? These are the examples for each and every crystal system, students. Hexagonal, graphite to ZnO CDS. Hexagonal, graphite is in hexagonal crystal structure. Graphite, ZnO, zinc oxide, CDS, cadmium sulfide. These are the examples of hexagonal, right? 3 more are there. Rhombohedral, monoclinic, triclinic. Rhombohedral, RH, simply I am giving you RH, rhombohedral. Examples are for rhombohedral are calcite. Its formula is CaCO3, calcium mineral, calcite. HGS, it is also a mercury mineral. Its name is what? Cinnabar. Its name is what, students? Cinnabar. These are in this particular crystalline structure, rhombohedral crystalline structure. For monoclinic and triclinic, I am going to give you some examples. For monoclinic and triclinic, I am going to give you some examples. Yes, for monoclinic, MC, monoclinic sulfur, that is the example. For triclinic, TC. For triclinic, the examples are Na2SO4, 10H2O, Na2SO4 dot 10H2O, Na2SO4 dot 10H2O, then K2Cr2O7. This is very important, students. K2Cr2O7. Yes, very important. Very important, Nana. So K2Cr2O7 crystalline structure checkmante. If they ask you what is the crystalline structure of K2Cr2O7, yes, this crystallizes in triclinic manner. Okay, just you have to memorize. And again CuSO4. Yes, this is the complete information about crystal systems, Bravais lattice and their parameters. Clear? So this is very essential information for your calculations, for your board examinations also. Yes, let me discuss some other points. Yes, 1 minute. Okay. Right. Okay, right. So, how many lattice points are there in simple cube, students? Simple cube lo lattice points. How many lattice points are there in simple cube? How many lattice points are there in a simple cube? 1 minute. How many lattice points are there in a simple cube? Lattice points only I am asking. Lattice points only what I am asking, not atoms. Not atoms. It is what simple cubic unit cell. Yes, 1, 2, 3, 4, 5, 6, 7, 8 lattice points are there in simple cube. Whereas in BCC there are 9 lattice points. In BCC there are 9 lattice points. In FCC, in face center there is an extra unit, lattice point is there. Okay, 8 plus 6 we are having how many? 8 plus 6, what are you having? 14 lattice points. In simple cube there are 8 lattice points. In BCC there are 8 plus 1, which is in body center, 9 lattice points. Whereas in FCC, students, FCC there are 8 plus 6 face centers, 14 lattice points. You getting my point? Yes, these are also somewhat needed data. This is also somewhat needed data for your calculations in solid state. Now again I am repeating. In simple cubic unit cell there are 8 lattice points. In body centered cubic unit cell there are 9 lattice points. In FCC there are 8 corners and 6 face centers. Totally 14 lattice points are present. You getting my point? Yes, this is also a very important data for your problems. Right? Yes, here contribution of each and every lattice point towards a unit cell, it is very important. Contribution of each and every lattice point towards a unit cell, it is very important, students. Suppose you take here, this is one cube. Which is attached to another cube like this. In 3-dimensional manner, it is attached with another cube. Here this face is somewhat, I just split these two faces, right? In other words, I am going to give you another idea. Yes, this unit cell is going to be repeated in all directions in the unit cell, right? You know that, right? Right. This unit cell is going to be repeated in all directions in the crystal lattice, right, students? That means if a lattice point is there means it is not strictly belongs to this unit cell only. Just some part only belongs to this unit cell. This much part is going to belongs to its unit cell. That is what only some part of the unit cell is belongs to this unit cell. Rest of the part, it is below half, right? Rest of the part, this part is belongs to other unit cells. This other rest of the part is belongs to other unit cells none. Okay, right. That means the contribution of this lattice point towards that unit cell is not completely 1. Its contribution is less than 1. Its contribution is less than 1. Suppose a unit cell, a lattice point is just inside the unit cell. A lattice point is inside the unit cell, middle of the unit cell, as this is completely belongs to the complete one unit cell which is present in your room. Right in the middle is there, means that lattice point is belongs to your room. But in your room, in corner, a lattice point is there, means yes, inside which is present in your room is belongs to your room, but rest of the part is belongs to in upstairs, otherwise the room which is connected to with other rooms. This room is which is connected to other rooms. That means this particular lattice point which is at corners is not belongs to this corner. 100% is not belongs to this corner, right? Some percentage only belongs to this corner. Rest of the percentages belongs to other unit cells also. So we have to identify the contribution of lattice point to corner. Contribution of lattice point to corner. Let me explain. Just you take this as a unit cell. Yes, 1 minute. Yes, this side you can insert an edge. Oppositely you can insert another edge. In this direction you will insert another edge. From backward you will insert another edge. 4 edges are inserted, right? And with 1, 2, 3, 4, 5, 6, we can insert 6 edges with symmetric separations. 1, 2 from back side and front side. 2, 3, 4, 5, 6. We can insert 6 edges, but contribution is not 1 by 6. Wait a minute. I am going to cut this. ఒక్క నిమిషం. Yes, this is what center of the unit cell, right? Center of the lattice point, right? Clear? Center of the lattice point. That one is center of the lattice point. This one. So from which side? From this side, one edge is contact to this center. From this opposite side, another edge will come. From this direction, another edge will come. From this direction, another edge will come to contact the center. This is another edge and this one is another edge. That means what is the contribution in the sense? We cut into half, right? We cut into half, right? Half into contribution of corner. This is half into. Yes, you see, what is the angle which is going to be maintained between two edges which are connected at center? It is 90 degrees, right? Is this 90 degrees or not? You take all the 6 edges. What is the angle which is going to be maintained inside the lattice point is 90 degrees only, which is present at corner. Right. So here, this is one edge. This is one edge. And this is another edge. What is the angle which is going to be maintained at the center of the lattice point? Is 90 degrees. You just compare this edge and this edge, 90 degrees again. Any two edges which are joined at the center of the lattice point, they are going to maintain 90 degrees of angle, and the total angle which is around this point is 360. You getting my point? This is nothing but contribution of a corner to the unit cell. Contribution of corner to the unit cell, students. Right. You calculate this. What it is? I think it is what? 4 times 1 by 2 into 1 by 4. So contribution of lattice point to the corner is 1 by 8. Contribution of lattice point to one unit cell. contribution of lattice point which is at corner. Contribution of lattice point which is at corner to the unit cell is 1 by 8th portion only. It is contributed to this unit cell. Rest of the portion is contributed to another unit cells. Another unit cells. Just keep this in your mind. When you assume a lattice point is here on the edge, a lattice point is on the edge. A lattice point is on the edge. That is nothing but lattice point is passes through the center of the center like this. Edge is passing through the lattice point like this. Here. This lattice point is on edge means what? This edge is passing through exactly to the center of lattice point, right? Like this, right? Here the angle is contribution, that's the contribution of edge lattice point. Half into, then angle maintained around the straight line is 180 by total angle at the lattice point, center of the lattice point is 360. Now it is 1 by 4. The lattice point which is going to contribute, to the unit cell which is on the edge is 1 by 4. Just keep this in your mind. What is the contribution of lattice point which is on the edge? What is the contribution of lattice point which is on the edge to the unit cell is? Half into, see, this edge is completely passing through the center like this. Here straight line is maintaining, around straight line the angle is 180 divided by total angle around the lattice point is 360. By calculating you will get what? 1 by 4. This is the contribution of edge center lattice point towards the unit cell. You getting my point? Of course, if it is in body center, contribution is 1. This is corner contribution. Corner lattice point contribution towards the unit cell. This is the edge lattice point contribution towards the unit cell. This is what? Body center contribution towards the unit cell. Body center lattice point contribution towards the unit cell. It is 1. And face center contribution is FCC contribution. Suppose you just assume if a lattice point is over there at the center of the face, you can easily find out half lattice point will come into this room, another half lattice point is come in other unit cell, right? This is what face center. Suppose here the lattice point is there, means half of the lattice point is in this unit cell, half of the lattice point will be in another unit cell, right? So FCC contribution is 1 by 2. Face centered, otherwise face centered unit cell contribution. Face centered lattice point contribution towards the unit cell. Face centered lattice point contribution towards the unit cell is half. Corner contribution is 1 by 8. Edge contribution is 1 by 4. Body contribution is 1. If a lattice point is, I am repeating once again, if a lattice point which is in corner, that contributes only 1 by part to one unit cell. 1 by 8th part to one unit cell. Getting my point? If a lattice point which is at corner, its contribution towards the unit cell is 1 by 8th part only. Right? If a lattice point which is on edge, its contribution towards the unit cell is 1 by 4th part. Rest of the part is with other unit cells. If a lattice point is at body center, this body center lattice point is completely belongs to this unit cell. So its contribution towards unit cell is completely, that is 1. Suppose a lattice point which is at the center of the face, its contribution towards one unit cell is half. another unit cell is half. These contributions are very important, students. These contributions are very important. By knowing these contributions only, we can find out the formula of a crystal or as a compound by means of given data. Okay, these contributions just keep in your mind. We'll meet in the next video, students. Thank you very much. Just memorize these contributions. How this is 1 by 8 explained, right? Each edge is maintaining 90 degrees at each and every center of lattice point. So half in the sense we cut it into half, right? Lattice point half cut chestene manaki we are going to visualize this. So half into each angle maintaining at the center is 90. When it is in corners, each edge is meet at the center are separated by 90 degrees. So each angle maintained 90 degrees divided by total angle around a corner. Otherwise, around a lattice center is 360. By calculating, we will get what? 1 by 8. This is the contribution of lattice point which is at corner towards the unit cell. Yes, like that. Here straight line is passing through the lattice point. Straight line is going to maintain 180 degrees and total angle is 360. Half into 180 by 360 you will get what? Contribution 1 by 4. Body center low. We are having lattice point means yes, that is belongs to complete unit cell. So its contribution is 1. If it is on the face center, so half of the lattice point is belongs to one unit cell. Half of the lattice point is belongs to another unit cell. That's it. You memorize all the contributions. We'll calculate some formulas in the next class. Thank you very much.